Good morning, ladies and gentlemen, and welcome to this short web series on how to utilize Mplus to run your very first structural equation model. My name is Llewellyn van Zyl, and I'm an assistant professor at the Human Performance Management Department at the University of Eindhoven. I'm also involved with the Optentia research program at the Northwest University in South Africa. So, before I start this lecture series, it's really important that you have a basic understanding of structural equation modeling. You don't need to have in-depth knowledge, but you should really understand the basics. What is a measurement model? What is a structural model? What is a regression? What is a correlation? It's really important that you have this in place, otherwise you might not get so much benefit out of this short web series. So, like I mentioned, the purpose of this web series is really to provide you with a very practical, step-by-step guide on how to run your first SEM analysis in Mplus. We'll be sticking to the basics. So the first thing that we will do, and we'll be running 4 specific lectures, it's very short. The first one is to really give you an introduction to Mplus and really have a solid foundation in terms of how the syntax works, how do we interpret the data, and then also give you a short overview of the data set that we'll be utilizing for the other videos. In lecture 2, we'll be talking about measurement models. And measurement models is basically various theoretical models that we have in place that we systematically compare with one another in order to figure out what is the best fitting model, theoretical model, for the data that we have. And we'll be utilizing what we call a confirmatory factor analytic approach. There are various ways that you can utilize measurement models, but this is the specific approach that we'll be utilizing. In lecture 3, we will then take the best fitting measurement model and we will then transform it into a structural model, a path model, a regression model, where we can physically determine the extent of the relationships between the factors. Once we have that, in the final video, we'll be talking about indirect effects. So we talk about mediation. So how does factor A, how does our independent variable relate to our outcome variable through our mediator? So how does the independent variable basically get translated through the mediator into the outcome variable? We'll be utilizing, I'll be showing you both testing some assumptions with the Baron and Kelly method, and I'll also show you how to estimate the indirect effects in Mplus. So, are you excited? I am. So let's see. Let's talk a little bit about Mplus. So the reason why you're probably here is to learn a little bit about how Mplus works, how to run your first analysis, what the syntax look like, but you've probably utilized other assessment measures, right? So you've basically used something like SPSS maybe AMOS, so you have some indication of a statistical analysis program. Where Mplus is a bit different, where it really is focused on structural equation modeling and various utilizations of it. So it's quite similar to Lisrel and AMOS in that respect, but it is also a little bit different. And I'm not going to go into the differences and the similarities between the different factors because that's not the purpose of this, but Mplus is a very powerful tool that addresses most of the limitations that other software programs, for example, have. So, just as a bit of a reminder, remember in structural equation modeling, certain little icons and certain little things mean specific aspects, right? So any circle, right? A circle is what represents a latent variable. Any square that we have represents an observed variable, something like an item that we've measured, something like gender maybe, or something like the first item on the life satisfaction scale. How satisfied are you with your overall life? Arrows with 2 sides, so dual pointing arrows, represent correlations or covariances, and an arrow with only 1 point indicates a regressive pathway. So this is just very important for you to kind of remember, because our models will always take this form. So what does an Mplus syntax structure look like? Every Mplus syntax that you'll be writing will have 6 to 7 kind of major headings. The first one is the title. The title we use to kind of just give our analysis a name, so that we can, when we have to look at it again later, so that we know what it is. And you can specify whatever you want in this part. The next part is a heading called data. Here we specify where the data that we're utilizing is located. So where can Mplus get the data from? In the variable command, it helps us to both list all of the factors in our data set, but also helps us to indicate what variables we will use for the analysis. Sometimes we have hundreds of factors in our data set, but we only want to use 3 of them. So in the command we also specify which ones, and here we also specify our missing values. Then we have the define command, and in this command it basically helps us to transform certain factors into other things. So we can create new factors out of other factors, for example. In the analysis command, here we specify what estimator we will use, and you'll know in structural equation modeling there's various estimation methods. So sometimes if you don't have a normal distribution, you want to use a different estimator, and it also indicates what type of analysis you can use, for example in EFA. Then we get to the core of our analysis, which is the model command, and here we specify the types of models that we will run, whether it is a structural model, a measurement model, an indirect effects model. We indicate in this part is the core of our analysis. And finally, we tell Mplus what type of output we want with the output command, and there's various output reports that you can get. So let's quickly run through each one of these just to give an example of what the syntax looks like. So this is kind of what Mplus syntax looks like. You can see there's a title, there's data, there's the variable names, and so on. A good point to just note is that anytime you put an exclamation point like here in front of text, it takes it out of the equation, so it becomes like a label. That's just an important thing to kind of like notice. Alright, ready? So the first part is our title. Now our title basically gives us a label for our analysis, and as you can see in the front, it's right at the top, and it helps us to kind of structure our little ideas around it. The next part is how we specify our data in our data command. Now the data command, we say file is, so what is the file that we're going to use, and we specify the specific data. If it's in the folder, the same folder where your syntaxes are, you can just specify the name of the file. If your data is located in another folder, you really have to specify the exact path like you would do in Windows. So for example, if it's on your desktop, it would be C drive / user / desktop / data. So it's really important that you just specify the exact path of your data. The next part is our variable command. Really important that any variable that you label needs to be a maximum of 8 characters. Otherwise Mplus doesn't read it. It will chop it off. Because you'll see when you get to the outputs, it has a very set character width. So 8, and also important that any line in Mplus cannot exceed 90 characters. But don't worry, it shows you in the corner how many characters you have used. So in this example, under our variable command, we have 2 commands. We have the names R command, 3 commands, sorry, the use variables command and the missing command. Now the names R is where you list every single factor in your dataset. So every column in your original SPSS or Excel datasheet, you list here. So in the exact same order that it was represented in your SPSS or Excel file. Every single last one, all 500 of them. And the next command is the use variables command, and this one tells us from all of these data sets, all of these data points that we have, which items, which factors are we going to utilize for our specific analysis. So in this case, out of gender, age, item 1, 2, and 3, we just want to use item 1, 2, and 3. Okay? And in the missing command, missing variables command, we labeled in SPSS or Excel everywhere where there was a missing value, we made it minus 999, and here we just tell Mplus what missing labels are attributed to. And you'll also notice after every statement there is a comma point. This is very important because this tells Mplus that this is the end of the section, end of the analysis. Okay, you got the data command in place. Let's go to the next one. The define command helps us to create new variables. So let's say, for example, in this scenario where we have item 1, 2, and 3, we want to create a mean score out of it. We first give it a label. We say engagement, for example, or whatever, is a function of item 1, 2, and 3 divided by 3. So we're just creating a mean score. And when you create this factor, you have to also then add it to this line, to the use variables line. Okay, it's really important, otherwise Mplus will give you an error. So you create a new variable here, and you can add it to your use variables command. So in the analysis command, this helps us to specify what type of analysis we're going to utilize. For our purposes, it's going to be straightforward. We have our estimator, which is in this case the maximum likelihood estimator. That assumes that data is normally distributed, and we estimate the amount of processes that your computer has. So if you don't know what your how many processes your computer have, just leave it out and it will utilize all of them. Okay, so Mplus has a whole bunch of estimators. As you can clearly see, MLM, maximum likelihood, robust MLM, and so on and so forth. So each one of these estimators have a certain function or certain thing that it compensates for. What's important for you is to kind of like know that maximum likelihood is the default. This assumes that the data is normally distributed. When your data is not normally distributed, we utilize either the MLM, where it basically kind of adjusts your chi-square for the deviations in multivariate normality, or we utilize MLR, which is a bit more robust in that sense. So for your purposes, those are the three estimators that you will probably use: ML, MLR, and MLM. Okay, so what does the actual model command, what's the statements that you can use? So there are three, in the model command, there are three things that you need to remember. It's very simplistic. We have what we call by statements, we have with statements, and we have on statements. By statements helps us to create latent factors. So it basically helps us to estimate which factors attribute to which latent variable. It basically means measured by. Okay, so in this case you will see engagement is measured by item 1, 2, and 3. And then it will create a latent variable called engagement. With kind of specifies either correlations or covariances depending on the type of analysis that you're running. So how it basically works is you say task performance is correlated with engagement and fit. Okay, so that's just a normal correlation, and it will correlate these with one another. This is important for your measurement model. So the by statements and the with statement is important for your measurement models. The on statement is important for your regression model, so for your structural model. And this is just basically reads something like task performance is regressed on engagement and fit. In other words, your outcome factor, right, is regressed on your two independent factors. Okay, pretty straightforward. We'll give you some examples in a minute, don't worry. This is kind of what it would look like. So an example of a by statement where you create these latent variables, we've got engagement is made up of item 1 and 3, task by 2, 4, and 6, and demands by 7, 8, and 9. So here you can basically see that engagement is made up of these two factors, demands, these two factors, task performance, these three factors. Now I didn't specify it in this sketch, otherwise it would get too complex, but every item also has an error variance attached to it. So you will also notice that there are correlations or covariances between these factors. You don't specify them. Mplus does this automatically in your measurement models. Okay, so you don't have to worry about that. What you'll also notice is that there is a little 1 on each one of these little factors. This helps us to estimate the rest of the factors, the rest of the loadings. Now Mplus does this by default, so every item that you specify as the first item, so here item 1 or item 4, item 7, will be constrained to be 1. This helps us then to kind of estimate the factor loadings based on that specific value. So it standardizes that loading and then it basically constrains them. But now we have a small little problem. If we run this model, you will know from parsonomy and model identification that we need at least a minimum of 3 items to kind of estimate the latent factor. But here we have engagement that is 2. So when you run the model, you get this error. Non-convergence, number of iterations exceeded. So how do we then go about fixing it, right? Okay, important is that we have to kind of move that 1, the variance that's estimated on item 1, we have to kind of take it out and constrain the factor, so engagement's variance to 1, right? We have to allow item 1 that was previously constrained to 1 to be freely estimated, right? And if that doesn't work, you can constrain the 2 paths to be equal. Once we constrain the 2 paths to be equal, we attribute the variance as 1 to engagement. It will then freely estimate the 2 factors. Okay, so these are the 3 steps that you can do to kind of help you to manipulate it a little bit to get your model to run. But it's always important when you do this that you specify it in your output. Now, important, when you freely estimate a factor, you put a little star on the item that you want to have freely estimated. And in this case, it's item 1 because this is the first factor that you specify there, the first observed variable. In order to fix your variance to 1, you put the latent variable that you've created and you put your little @1 sign. Easy enough. And to constrain the 2 paths to be equal, you just say item 1 and 2 and they are called A. And the A doesn't matter, you can call it whatever you want. You can give it a label, you can give it a name, you can give it a number, doesn't matter. Okay, this will help you to run your model. So we can also make it a little bit more complex. So this is just a normal three-factor model with 3 different components. And also one thing I forgot to mention is that you always put all 3 of these factors, all of your factors, your CFAs, you put together in the same equation, right, on the same page basically. Never do a separate CFA for each of the factors because you lose variance, you lose interactions. In this case, for example, with engagement, it would borrow some degrees of freedom from demands and task performance in order to help to estimate that model. So it's important to have all 3 of these things always estimated at the same time. Okay. So now we can also create a second order latent factor, right, out of this. So we can also say that maybe happiness is made up of meaning, engagement, and pleasure with all of these items. We can add another factor there called happiness by engagement, meaning, and pleasure. So by the latent variables that we've created. So we can also estimate that. And if you run into the same problem in terms of what we did with engagement, you manage it in exactly the same way. If you have no convergence, you constrain, you release this path, you constrain happiness to 1, you constrain all of the factors to be together, and you freely estimate meaning. Okay, so now we get to the with statements. Like I said, Mplus automatically does this in the background for your measurement models, but you can also specify other correlations, for example, task performance with engagement and demand, and then it would estimate that for you. So now that we have that in place, we go to the next one, which is our on statement. And basically all that we say here is task performance. So our dependent variable is regressed on, engagement, and demands. And this is what it looks like. So engagement and demands predicts task performance. Okay, pretty straightforward. The last thing, and this is what we do for our structural models. The last thing that we do is we want to estimate some mediation. Now this becomes a little bit more complex, but not too much. So you'll first see still our original statement there. All that we do now is we regress engagement on demands. So demands leads to engagement, engagement leads to task performance. We estimate that, we see if it works. And we add an extra component after the model command, which we call model indirect. So this helps us to estimate the mediation, because mediation is called indirect effects. And here we say task performance, our dependent variable, is indirectly affected by the mediator and the independent variable. It's important to keep it in this structure because Mplus reads it as this: dv, mediator, iv. Okay? Pretty straightforward, right? I knew it. You guys are smart. So now, once we estimate this stuff, we kind of have to figure out a way to help us understand what model is actually the best. And we utilize some fit statistics from Hugh and Bentler. They basically said that there are some absolute fit, approximate fit, and incremental fit indices that we utilize, and we use all of them, right? So it's not just one of them, we use the combination of all of them. So chi-square is an indication of model misfit, so it basically tells us that the extent towards which our data doesn't fit our model. So in the perfect world, we want a 0 chi-square, right? But we'll never get that. And we want to have a significant difference. So it must be non-significant, and we have to have a very low value when we compare the different models with one another. So the same thing with SRMR. Here we want a value that's smaller than 0.8. The same thing with REMISA. Here we want a value smaller than 0.8. We want the confidence interval to not include 0. Important. And finally, for incremental fit, and this is usually the thing you look at first, is these incremental fit indices need to be bigger than 0.9. So anything below that doesn't indicate fit. We also look at, and I'm not mentioning it here, but we also look at AIC and BIC values. I'll show you that in our actual model, but all that you do here is the same with chi-square. AIC and a BIC value that's lower compared to another model will give you an indication of good fit. However, very important to understand that these fit indices, people use them very prolifically and just to indicate fit, doesn't really give us accurate indication of model fit. Why? Because we know that models where items load very high on a certain factor, so if you have items very low on factors, so items that load like 0.4 or anything to that effect, will create a higher level of variation in the model, and therefore our model is more likely to fit. So a poor measurement model, actually a poor instrument, could provide you with excellent results, right? Excellent fit statistics. So never just look at the fit statistics in isolation, always look at measurement quality as well. So we first check, are these things in place? If they are, we go to our measurement, our model statistics, and we look at, are the items, do they load significantly? Is there any negative error variances, and etc. So we kind of have to look at those aspects as an indication. There are some articles that I'll also mention in the comments that can give you a nice brief high-level explanation of this, as well as a non-technical primer on measurement quality. Okay, let's look at this output quickly. So let's first look at the chi-square, the TFI, the CFI, SRMR, and etc. Take a minute, pause the video, and tell me whether or not you think this is a good fit. So write down whether you think chi-square is correct, TLI, CFI, SRMR, and REMISA, if it meets all of the criteria. Okay, welcome back. So let's see what we wrote. So CLI and TFI is bigger than 0.9. Yay us, good model. SRMR, smaller than 0.8. Great job, boys. We got it. Remisa is smaller than 0.5. The confidence interval does not include 0. And it's non-significant. So, we have a good model, right? Chi-square is also low. Problem is that chi-square is significant, which means there is a significant difference. So, what do we do? Now, the point here is that in this specific case, I think the sample is like 300 or something, and chi-square is unfortunately a function of model complexity and sample size. So on small samples that's not very complex, you might get this value. But that is not a problem. The big thing here is that at least we have multiple other indicators that help us to understand whether or not our model fits or not. So if one is not in place, you can still utilize it, but just give an argument or reasoning why. Okay, so that is that for Mplus. This is going to be the theoretical model that we'll be testing. Remember, with structured equation modeling, it's basically hypothesis testing. So it is a theory-driven assumption that we have. It's not exploratory, and we want to figure out a specific relationship between specific factors. So it is always theory-driven. So our theory tells us, in this case, in our data set, that we have person-environment fit, happiness, and task performance. So if a person fits his job, he's going to be happier, and if he's happier, he's going to perform better, right? The three instruments that we used was the person environment fit scale from Cable and Roux, the orientations to happiness scale from Seligman, and the task performance one from Koopman. So from this scale, we can see that the scale measures person environment fit, but it's also made up of three other latent factors: person environment fit, need supply fit, and demandability fit. So the questionnaire will have items for each one of these factors. Happiness is made up of three factors actually: pleasure, meaning, and engagement. However, you can't build lasting happiness on the pleasure component, so we've taken this out, and we'll just be looking at two routes to happiness, which is engagement and meaning. And the instrument measures these two factors, and each factor will have specific items attached to it. And the same thing with Koopman scale. Task performance means how fast and how accurate can I perform my duties, how well do I perform them. We want to test in the next videos two basic assumptions. We want to determine the relationship between person-environment fit, these routes to happiness, and task performance. We'll first be estimating 4 measurement models, so 4 models that we can compare with one another. That's theory-driven, not just random models that we come up from our head. And from these theory-driven models, we find what's the best fitting model for our data, and we then utilize that for our structural model, which helps us to determine the relationships. Once we have this in place, the next assumption that we want to test is the indirect effect, so the mediating mechanisms. And here we want to see how does the routes to happiness indirectly affect the relationship between person-environment fit and task performance. And we just basically expand our structural model in this effect. So our data, basically, we utilize the cross-sectional survey-based design in the Twente region in the Netherlands. So we basically had 5 companies. We asked all these employees to complete our questionnaires, and we got about 311 people from Germany and the Netherlands. So because the Twente region is basically filled with or fueled by Germans, because it's close proximity to the border. And this is kind of like the item labels for each of the factors that we have in our data set. So we've got person organization fit is made up of item 1, 4, and 7, need supply 2, 5, and 8, and so on and so forth. So this is how theoretically how the instrument measures each of these factors. Same with engagement, same with task performance. We also have some demographic variables in place, like gender, age, language, level of education, and etc. So this is our data set. Now, it's over to you, because I want you to go and given everything that we've learned now, just type down this model command. So type down a structural model, so with an on statement for this picture. Okay, use the by statements to create our latent factors, and use the on statement to create our regression factors. The memo will be uploaded somewhere. So, good luck.